Welcome. So we're going to continue our study of undirected graphs by looking at bipartite graphs. And today we're going to create an implementation of an algorithm to determine if a graph is bipartite. So today's plan is first to recall the concept of a connected component, and then also to recall what a bipartite graph is. Then we'll review the implementation of cc.java, which is the connected components implementation provided in the algorithms course jar file. And then we're going to implement a program to determine if a graph is bipartite. So to recall, a graph is connected if you can reach every node from every other node. So for example here, if I began at node 3, I could reach every node in the graph by either a DFS or breadth first search traversal. A graph is not connected if this is not true. So for example, from node 8, I could only reach nodes 9 and 7. So we call each of these a component of the graph. So this graph has 4 components, and we can refer to them as connected components. So the question is, how can we determine which nodes are in each component, or which nodes are connected to each other? So again, this is implemented in cc.java. So we're going to go make a copy of that now and read through it to make sure we understand how that works, because then we're going to use that for our implementation of determining if a graph is bipartite. The general idea is that we're going to create a new array. Each position in the array corresponds to a node. And for that node, we're going to record what component that node is in. All the components will be integer values. And then we're going to start a DFS search from each and every node in the graph if that node is not already marked in a component. And then for each node that's connected to the node that we just found, we will assign it the same component number. So let's go over into IntelliJ and go take a look at cc.java. So you can make a copy of this. So make a copy of cc.java. This is in the alg4 jar file. So just down edu princeton cs alg4. And I'll just paste it up into my source just so it's easier to find. And we'll just leave the same name. Okay, so let's look through cc.java and just get a feel for how it works. So we need to keep track of which component each node is in. So that's what the ID array does. And then we also just want to keep track of the number of vertices in each component. So that's what size will do. So if we look at the constructor takes a graph that's already been loaded from a file. We'll create all 3 of our arrays. Now the size is the interesting one. If a graph has no edges, then the number of components will be equal to the number of vertices in the graph. So that's the worst case. So they create an array for size that's the number of vertices. So the interesting part now is we're going to go through every vertex in the graph. And if it has not been visited yet, we'll do a DFS. Now as we scroll down, we'll note that there's a different constructor. So currently we're doing unweighted graphs. They've also implemented it for weighted graphs, but we're just going to focus on the unweighted one. So inside the DFS, so we already know that's not marked because that was a check prior to coming into DFS. We'll now mark this node as marked. Since it hadn't been visited previously, this is going to be the first time that we're visiting it, so it's going to get a new component number. Count is a global variable that was set up above that starts at 0. And so the first node that we visit is going to be in component 0. The second time we do a DFS, count would have been increased, so it'll give a different count number. Now count is incremented up in the constructor, and we can peek at that in a moment. And then likewise, we're going to keep track of the number of nodes in each component. So we'll go into the size array and just say, okay, for this component, I increased by 1. I probably would not have called count. I might have called this component number or something like that just for clarity. And then we're going to do a standard depth first search from this node. So each node that we visit will basically get the same component number. So this will keep going to every node that we're connected to, and so they will get all the same component number. When this returns, when we can't reach any other connected nodes, we'll come back to the constructor. Count will increase by 1. And then we'll go to the next vertex to begin with. Well, if we haven't visited it as a result of that first depth first search, we'll visit it now, but now count will be 1, component number will be 1. And so then we'll reach all the things connected to that second one. And by this process, we will see all the nodes that are connected. So let's demo this. So let's go ahead and run it. And we're going to need to set up the argument just like last time. So I'm going to run it so we get a configuration, and then we can change it. There are a couple new data files to mention that you can grab from Schoology. We have 2 bipartite files, 2 connected component ones, and then 2 that are not bipartite. And then for each of these, you'll see a pair of files. One is formatted in the CS Academy format so we can see them visually, and the other is formatted in the format that is required by this algorithms course. Okay, so let's go into edit configuration, and we are going to do the connected components like we had seen before in the PowerPoint. So, okay, so the argument will be data U10 connected components. You can hit OK, and then go back and run it. And you'll have a list of nodes. So 0, 3, and 4 is in one component. And so if we go back to look at the graph that we had, we'll say 0, 3, and 4 is in one component, 5 is in a different component, and 7, 8, and 9 are in a third component. So you can compare that this output matches the visual graph that we had produced previously. Okay, so now that we understand how that works, let's go and talk about a bipartite graph. So again, a bipartite graph is a graph that can be have all the nodes subdivided into 2 sets such that each node in a given set is only connected to nodes in the other set. And so we would say that we can color the graph with 2 colors such that 2 nodes with the same color are never connected to each other. So our algorithm is actually going to be surprisingly similar to cc.java. But this time, each time we begin a depth first search, we'll assign the first node a given color. Let's call it blue. And then for each subsequent node in that component that we visit, we will assign it the opposite color of the node that we're currently on. So if we're in a node of blue color, we'll assign the next one red. And then if we're in a red node and when we visit another node, we will assign that new node blue. Each time we visit a node, if it is already colored, we're just going to make sure that the color that is already colored is the color that matches what we expected it to be. So if it was previously colored red, when we reach it from a different direction, we want to still make sure it should be red and that this direction doesn't think it should be blue. So let's watch a little video on how this, an illustration of this, and then we shall implement it. So let's illustrate the algorithm for determining if a graph is bipartite. And recall, a bipartite graph is a graph that can be colored with 2 colors such that no nodes are adjacent to a node of the same color. So this is going to be a depth first search where we can begin at any node. So let's just say we begin at node 1, and we're going to assign it an arbitrary color. We'll assign it blue. From 1, we will then do a depth first search to all of its adjacent nodes. In this case, 3 is the only adjacent node. And so then we will assign 3 the opposite color. We will then plan to visit all of the nodes connected to us via depth first search. So let's go to 2 first, since it's the lower one. Since it's uncolored, we'll assign it blue. Now 2 things happen here. We're going to visit all the nodes connected to us as well, but we will also kind of visit, so we'll first visit 3, we'll go back this way, and check what color that is. Okay, since I'm blue, let's make sure that the one that's already colored is red, and that's fine. And so then we'll visit to the right, and we're going to visit the 4, and we'll say, okay, the 4, we're going to assign that one a red because it's opposite of blue. Following along again, we'll verify from 4 to 2 to make sure our 2 is blue, make sure it's the opposite color. And then we'll go to 5, and 5 will get assigned the color blue. And then finally, finish the depth first search. The 5 is going to visit the 3 and verify that 3 is the opposite color from 5. So the main graph, or this connected component, has finished. Then we will then continue with the other component. So in this case, again, we'll start with the first color. So 6 will turn to blue, and then 7 will receive red. So this is an example of a graph that's bipartite. We were able to color it with 2 colors. So let's illustrate the same thing again. If we start it with 1, doing a depth first search, that guy will become blue. He'll visit to his right and set 2 to red. A depth first search again, so 2 will then go to its lowest connected neighbor first. So this will be set to blue. And then the 4 will do a depth first search and can set each of these to red. When we get to 5, he will also try to do a depth first search, and so he will traverse down this edge. And in traversing, he'll see that 2 is already colored, so he'll then compare the color of 2 to the color that 5 expects it should be. Well, since 5 is red, it expects that 2 should be blue. But in this case, we see that 2 has already been colored red, so the algorithm returns that this is not a bipartite graph. And that is the algorithm that we will implement. Okay, so let's jump back to IntelliJ. And so to implement this, we're going to make a copy of CC. So let's do copy and paste, and I'll call this bipartite. Okay, so let's go through the implementation of how for bipartite. The first thing we're going to need to do is just create some variables, some static variables. So public static final int, and we'll have a color none. So this is going to, so if a node is a value 0 for color, it means it has no color yet. And then we'll have 2 arbitrary colors. We'll just call them color 1 and 2. You can think of them as like red and blue. But those 1 and 2 are our 2 colors. We're going to need to keep track of the colors for each node. So we're going to have a new color array. And then we're also going to keep track of whether the graph as a whole is bipartite. So that'll be a Boolean. So coming down to our constructor, for the color array, it's going to be just like the size and the ID array. So it's going to be an array of ints. Since it's an array of ints, it defaults to all zeros, which means it defaults to no colors. Bipartite, we are going to default to true. We're going to make an assumption that it is bipartite, and if at some point we find that it is not bipartite, then we'll record that. Everything else, one last thing in the constructor. So we're going to do a DFS for every vertex, starting from every vertex in the graph. Well, an earlier DFS might have already visited a node, so we will not start a DFS if we've from a node that's already been marked. So essentially, we will start a DFS once for each once in every connected component, and so it doesn't matter what color we assign to the first node that we visit in a connected component, but we need to give it a color. So we'll say color sub v, and we'll give it color 1. So after that, we can go down to the DFS. By the way, we'll notice in here that there's some edge-weighted implementations as well. We're not going to deal with edge-weighted graphs. So we can get rid of the constructor and the DFS related to edge-weighted. They could stay, they can go. I just got rid of them for clarity. Okay, so inside DFS, everything is the same until we're inside the for loop. So again, for starting from each node in the graph, this up in constructor, we are iterating through and starting a DFS, right? And basically we start one DFS from each connected component, and then from from a given component, then we're going to visit all nodes that are connected to it. So the first thing we're going to do is we're going to say, hey, have we visited before? Is this node W marked? If it's not marked, well, then we need to assign it a color. And so if node V, our current node, is say color 1, we want to set the color for W to color 2, and vice versa. So we can say color W equals, and we'll do a little expression here. So color V equals color 1. And then basically we'll say, okay, if it was color 1, set W to color 2, otherwise set to color 1. Because V is either 1 or 2, so set W to the opposite. Now the interesting case comes up if it was already marked. So if the W was already marked, we want to make sure that the color of W doesn't match the color of V, because W should be the opposite color from V. So we can just say else if color W equals color V, this is the bad case, bipartite equals false. So if we ever run into this case, this is where we've determined that it's not bipartite. So the last thing we need to do is just create our accessor, so we can just return this. So is bipartite. Bipartite. So let's go down to main. And down in main, we're just going to indicate that something is bipartite or not. And we'll do true or false. And we can run this and see if it works. So if we go up to run, and we have two data files that we can work from. So we have the bipartite and the not bipartite. So again, you're going to need to do the edit configuration. So our program arguments will be data U10 and bipartite.text, and that should return true. And let's check off the box at the bottom because we're going to run this with different arguments. You hit OK, and then you can go ahead and run it. And it should pop up the box again because we checked that off. Go ahead and hit run. And it should indicate the components again, and it should indicate that it's bipartite. And then let's run it again. And these are the graphs. These are the same graphs that we just drew when we were doing our lesson. So we can compare back to those. And not bipartite, and you can run it. And it should indicate that this graph is not bipartite. And that's it. So hopefully today the concept of connected components and bipartite graphs makes sense. And we'll continue on next time.